Hey y'all, remember when I told you that dy dx notation was going to come in handy because one day you were going to have to split it up? Well, today is that magical day. We'll get there in just a little bit, but right now, let's focus on the fact that we've seen that slope fields give us a visual representation of the solutions to a differential equation. In other words, it gives us all the possible functions with the same derivative. The question is, how do we find the equations of those solutions? So let's use our knowledge of antiderivatives to answer the following. So if we know dy dx is x cubed minus 4, what's y? In other words, what's the original function? Well, we know the original function has, this first term has a degree of 4, which means we put a 1/4 out in front, minus 4x, and then don't forget your plus c there. For letter B, we've got this down on the bottom. Remember, the antiderivative is going to be the natural log of 2t minus 3. And then because of the chain rule, if we had a 2 on the inside, we need a 1/2 to balance it out, plus c. Over here, if we know that the derivative is secant squared of y, the antiderivative is tangent y plus c. Notice that because we're working with respect to y, that we're using the variable y here. And then finally, how do we work backwards from this? Again, this is 1/2 the natural log of 2t minus 3 plus c. So we've looked at it in different ways. We've looked at these as working backwards from integrals, and we've looked at them from working backwards from that Leibniz notation of a derivative. Either way, we're working backwards. We're given a derivative, and we're finding what the OG function is. But let's consider something more complex. How do we find the OG function if the derivative is x times y? Let's describe in words what that means. That means the slope at each point on the original graph will be the product of the x and y. So what makes this different than the differential equations that you were given in question 1? If we look in question 1, all of our answers have a single variable. Here we have x's by itself, here we have a y by itself, here we have t by itself, same deal here. We have one variable in all of our derivatives. Sorry, I highlighted the answers, but that's true in the originals as well. If we look at the originals, there's one variable. But if we look here at this derivative, there's two variables. So that's what's different. The slope depends on two variables, not just one. The slope depends on two variables. So here's the slope field for the differential equation. All of these slopes are x times y. So sketch 3 possible solution curves. Now your answers will vary because you might draw ones that are different than me, but I'll sketch 3 for you just for fun. So here, for example, we could have this, and remember that these slope fields are like magnetic fields or like currents. So whatever you drop in the water is going to follow the current. So Here are the different possible graphs we could have that have a derivative of x times y. In order to solve this differential equation, just like we worked backwards and found all of these solutions to all of these derivatives, the problem is we'll need one variable of integration. If we want to integrate, we need to focus on one variable, like that top example we did. But currently, we're focused on two variables, x and y. So to navigate this, we're going to do something called separation of variables. So we will separate the variables. So all of our x's are on one side and all of our y's are on the other side. So for now, we'll treat dy dx as separate quantities that can be manipulated. So this is that magical moment where we're going to be able to take that dy dx and split it up. So here's how we're going to do it. We're going to rewrite our differential equation so that y terms are on the left and x terms are on the right. And we can do that by splitting up this dy dx. And that feels kind of weird because so far dy dx was notation. It was never a fraction. But guess what? Now we're going to treat it like a fraction. So here's what we're going to do. Let's get this dx to the other side. And we're going to do that with multiplication. So in your mind, you don't have to write this part, but I want to show you. In your mind, we're going to multiply both sides by dx. So here our dx is going to divide away, and our next step will be dy equals xy dx. Now the next step we're going to do is get all of our y's on the other side, because now all of our x terms are on the left. We've got our x over here, we got our dx over here, we're good there. But our y needs to get to the other side. So how do we get it to the other side? We're going to divide it away. So then these will divide away, and then we will have 1 over y dy equals x dx. And suddenly we have one variable on the left, we have all our y's on the left, and we have all our x's on the right. Now we can integrate both sides. So what we can do is we can take this equation on the left, 1 over y dy, which equals x dx. I'm sorry about the announcement. Hang on.
Montez Austin and Ali Farman. If you can hear this, please go to the back by the 801 pod. Your transportation is here early.
Okay,
Thank you.
so we're going to integrate both sides of this, and I left some room on both sides. Oh, wait, we already have the dy, so I left entirely too much room. So we're going to integrate over here, and we're going to integrate over here. That's okay. It's okay that we left some extra room. No big deal. So let's integrate this side first. We're going to integrate 1 over y. So what function has a derivative of 1 over y? That function is, of course, natural log of y plus c. Now let's integrate this side. What function has a derivative of x? 1/2 x, or sorry, yikes, 1/2 x squared plus c. So you might be saying, there's a c on both sides. Maybe you didn't squeak just as intensely as I just did. I hope you're laughing. We have a plus c over here and a plus c over here. It's not necessary to have it on both sides because this means plus any possible number plus any other possible number. So if we call this C1 and we call this C2, we can just combine them on the same side. Because what is any number and any number combined? Yep, you guessed it, it's any number. So we can rewrite this a little nicer as the natural log of y equals 1/2 x squared plus c. You don't have to have a constant on both sides. You can just combine your constants over here. Now, why did I choose to combine them on the right side? Because our ultimate goal is going to be solving for y, and this allowed us to move closer to getting y by itself. So instead of having a constant on both sides, it's like having infinity on both sides. You don't need infinity on both sides. You can just combine them on one side because c represents any possible number that you could add or subtract. So we're good there. Our final step is to solve for y. So let's get y by itself. So let's copy down natural log of y equals 1/2 x squared plus c. So now we're going to solve. And to do that, we're going to undo the natural log that the y is in. So you might have to think back to your pre-cal or your math 3 days, but we undo a log with an exponent. And specifically, we undo a natural log with an exponent that has a base of e. So what we're going to do is a process called exponentiating. And what that means is we're going to turn each side of this equation into a little baby exponent. And how do we do that? With a big base. So now we are now raising e to that power, and we're going to do it on both sides. Why is this helpful? Well, I wrote these e's a little too big just to be goofy, but I wanted to show you that exponents and logs undo each other, and that will leave us with y by itself. So over here, we're going to have y by itself. But on the right side, we're not going to have a natural log for this e to cancel out with. So we're going to have to leave it as is. So we're going to have, oh, I dropped the absolute value on accident. Oops, sorry guys. So the absolute value of e to the 1/2 x squared plus c. So now we're going to do plus or minus. So y equals plus or minus e to the 1/2 x squared plus c. Now, a lot of times you will see this split up, but before we look at this split up, I want to talk about this answer. It says, how does this relate to your work in 2B? Well, what I'm getting at specifically is this plus or minus up here. If we scroll up to 2B, you did a couple sketches. What did you notice about your sketches? You probably got some functions that were positive above the x-axis and some functions that were negative below the x-axis. That is captured by the plus or minus in your formula. So that was the takeaway from this, is I wanted you to recognize that this plus or minus shows you that you could have some positive or negative curves that fit this. So here's the other way that you might see this written sometimes. When you have a plus up here, when you've added exponents together, it means that in a previous step, you would have had y equals plus or minus e to the 1/2 x squared times plus or minus e to the c power. What this means is e raised to any possible constant. So this is a little conceptually hard to grasp, but here's what I want you to know. What is e raised to any constant? Well, it's just going to be another constant. So instead of writing e to the c power, we can just write this as its own c. Again, it's like thinking about e to infinity is just infinity, because e to an infinite power is just going to be more of infiniteness. So e to some constant is just going to be more constantness. So you could write this as plus or minus e to the 1/2 x squared, and then ultimately you would end up writing this as y equals plus or minus c e to the 1/2 x squared. You're going to see this a lot in the future, where this c comes from being added up here in the exponent. It's because if we think of that as e to the c, it just comes and lives down in the front. I know that you might feel a little shaky about that right now, but you're going to see that so much as the unit progresses, you're going to get more comfortable with it. Okay, so here is us formalizing what we've been talking about. Here's what we do when we solve a differential equation in the form dy dx equals some function in terms of x times some function in terms of y. We will start by using separation of variables. We're going to get all the x stuff on one side and all the y stuff on the other side. So we're going to separate. We're going to get all our x's on one side and all our y's on the other. Then we're going to integrate. Don't forget your plus c, but you only have to do that on one side. You don't have to add a constant to both sides. And then finally, isolate. In other words, get y by itself and look out for plus or minus in solutions. You're going to see that when you've got natural log and absolute value and you solve for y, you're going to want to make sure that when you undo the absolute values, and I got caught up here, I forgot to copy down the absolute value bars, but that's going to result in a plus or minus. So make sure that you're careful with that. So here are some examples. We're just going to do 3 and then we're going to be done. So hang in there. We're going to use separation of variables to find the general solution to the differential equation. So let's start here. Here, our x's and y's are all mixed together. So our step 1 is going to be to separate. 9 times out of 10, y'all, your first step is going to be to multiply both sides by dx to get it over on the right side. So we're going to have dy equals 3y dx. So now you've got your x over on this side. And even though this 3 could go either way, I like to leave it on the right side. The reason is your goal is to get y by itself eventually, so leave as much on the right side as you can. Now we want to get y on the other side, so we're going to divide both sides by y. So we're going to have 1 over y dy equals 3 dx. Now it's time for step 2, which is integrate. We're going to integrate the left, integrate the right. So integrate the left, natural log of the absolute value of y, not x, equals 3x plus c. We don't have to put plus c on both sides. It's not wrong, but it is redundant because when we combine our c's, it would just be more c's. Now it's time for step 3, which is get y by itself. So first we want to get rid of the natural log. We undo log with exponents, so we're going to raise both sides. I'm going to erase that 3 because I don't like it. We're going to take this side, and we're going to make that green bit an exponent. We now have e being raised to this power. So we're going to do the same thing on the other side. We're going to have e raised to this power. So e and the natural log undo each other. And so we will now have the absolute value of y is equal to e to the 3x plus c. That e is being raised to that entire power. Then we're going to undo the absolute value, y equals plus or minus e to the 3x plus c. And then what we talked about earlier is if you ever see a plus c out here, essentially what's happening, and you don't have to write this every time, I just want to show you here, it's just showing you plus or minus e to the 3x times e to the c power. And because e to the c is just another way of saying c, because e to any constant is just going to be a constant, more often than not, you'll see this as plus or minus c e to the 3x. And you know what's even crazier is you can even get rid of the plus or minus because c could be positive or negative already. So the plus or minus is redundant, although I would never mark off for it. Okay, let's try another one. Step 1, we're going to separate our x's and y's. So again, we want to get this dx to the other side. So we're going to multiply it on both sides. So we are going to have dy equals x over y dx. So now we are going to get y on the other side. Now notice y is being divided. So how do we undo division by y? That's right, we multiply. So we're going to have y dy equals x dx. So this one's pretty cute. Now we're going to integrate both sides. Don't forget your plus c, but remember you only have to put it on one side. So we're going to integrate, So we're going to have y 1/2 y squared, and then the implied plus c, but you only have to put it on one side, equals 1/2 x squared plus c. Finally, last but not least, we're going to solve for y. So first we're going to undo the 1/2 by multiplying everything through by 2. So we're going to have y squared equals x squared plus, and y'all, two groups of any constant is still just a constant. I know it's weird, but think about it like 2 times infinity is still infinity, right? So 2 times a constant is still just the constant. So you don't have to say 2c. Now, finally, we're going to take the square root of both sides. So y equals plus or minus the square root of x squared plus c. All right, example 1 done. Let's try example 2. What is the general solution to the differential equation? So this guy is pretty crazy looking, but we're going to handle it the same way we did before. We're going to do our steps. So step 1 is we're going to get all our x's on the right and all our y's on the left. So we're going to start by multiplying both sides by dx. So we're going to have dy is equal to y squared minus y squared times sine of x, and then that whole quantity is being multiplied by dx. Okay, this next part, you got to be careful because we want to get our y's on the other side. But there is a y term here and a y term here. So before we divide, let's factor it out. Let's see what we're doing. We can rewrite this as dy is equal to, we can factor out y squared, and then we can have 1 minus sine of x dx. So that's going to help us out because now we can see we're dividing that y squared out of both sides. So in our next step, we're going to have 1 over y squared dy equals 1 minus sine of x dx. So now we are done with step 1. So now it's time to integrate both sides. So what we can do is integrate this side and integrate this side. That's our step 2. And just for a little bit of ease, it's going to work either way, but you can also write y to the negative 2 power. That's the same thing as dividing 1 by y squared. So how do we integrate this? Remember, when we integrate, we take whatever the exponent is and we go up 1. So our new exponent is going to be negative 1, and then sorry, I don't want this to look like multiplying by 2. This is step 2. So we're going to put a negative out in front to correct that, equals, and then we're going to integrate 1, which is x. We're going to integrate negative sine, which is positive cosine, and then don't forget your plus c. So now our job is going to be to get y by itself. So one way that I think is easy to do this, to get y by itself, and I know we've kind of gone back and forth here, but you can do whatever makes you happy, is to write this as negative 1 over y equals x plus cosine x plus c. And here's why I wrote it like this with this weird gap, is because if we want to, we can put this right side over 1, and that makes solving for y really easy. We can flip both sides over. So if we flip this side over and make it negative at the same time, if we flip that side over and make it negative, we're going to end up with a positive y. And now we're going to flip this side over and make it negative, and we're going to have negative 1 over x plus cosine of x plus c. There's other algebraic ways to do this. Technically, if you had this, you could also diagonally multiply. So you can multiply this way and then multiply this way and solve for y like that. You know what? I'm just going to show it just for those of you who are like, what is this flipping business she just did? I want to make sure you're okay. So if we diagonally multiply, we'll have y times x plus cosine of x plus c equals negative 1. So now to get y by itself, we're going to divide both sides by that whole mess. So negative 1 over x plus cosine of x plus c. So whether you diagonally multiply or whether you followed the flipping and changing the sign, either way, you're going to end up with this general solution. All right. So with cross multiplying in mind, let's do this last one. we're going to solve for the general solution. So we want to get our dx's on both sides and our dy's on the other side. So you can show this all drawn out, which I'm going to do for those of you who benefit from that. But you can also recognize if I multiply both sides by dx, I'm going to have what I need over here. And if I multiply both sides by sine of y, I'm going to have what I need over here. So if you can recognize a little cross multiplying that happens, if you multiply these guys together and these guys together, that works for me. But if you're like, what is this? This is already enough stuff, then don't worry about it. Whoa, pen went crazy. All right, so we've got dy, pen went crazy again. We've got dy dx equals xe to the x squared all over sine of y. So let's start by multiplying both sides by dx. So we're going to get dy equals xe to the x squared over sine of y. Yeah, I don't know what's up with my pen right now. There we go. Times dx. So we've got all of our x stuff over here. We got this, we got this. So how do we undo division by sine of y? We're going to multiply it on both sides. So sine of y dy equals xe to the x squared dx. Okay, so now it's time to integrate. So we're going to integrate both sides. And so over here on the left, the integral of sine is negative cosine of y. No big deal. Here's where you might get a little bit grumpy with me, but you're going to be okay. This requires u substitution. And the reason why is because we've got a function inside of a function. Here we've got this little baby x squared, but luckily its derivative is on the scene. There's its derivative, almost. The derivative is 2x. We wish the 2x was there, so we're going to do a little bit of an adjustment. So I'm going to go out to the side and do this. The integral of xe to the x squared dx. So I'm going to make my u x squared, and I'm going to make my du 2x dx. So I wish that 2x was on the scene. It almost is. Oops, I erased it on accident. Now it's not at all. Hang on. There we go. So it's almost on the scene, but in order to get the 2x that I want, I need to put a 2 here. But I can't just go changing functions all willy-nilly. I need to correct it with a 1/2. So now I can rewrite this function, and I can write this as the integral of, or 1/2 times the integral of, I've got my 2x and my dx together make du, so I'm going to have e to the u du. And the integral of that is 1/2 e to the u plus c, of course. And then substituting our x's back in there, 1/2 e to the x squared plus c. So I'm going to come back over here and have 1/2 e to the x squared plus c. All right, so now our final step is solving for y, and we don't have far to go. The first thing we need to do is undo this negative, so we're going to multiply everything through by a negative. So we're going to have positive cosine of y equals negative 1/2 e to the x squared plus c. Now, if you're like, why didn't you write minus c? It's because it doesn't matter. C is a concept. It's every constant in the world. So this already encompasses all the positive and the negative numbers. So there's no reason to worry about a sign with it. So now finally, we're going to undo cosine. So how do we undo cosine? We're going to use inverse cosine or arc cosine. So y is equal to arc cosine, negative 1/2 e to the x squared plus c. Whoa,